let's talk about how these VPNs actually can protect your stuff, right? What they do is a VPN, and listen, we're going to focus on IPsec VPNs, okay? It's because they're taking over the world. This is the technology that is being standardized when you want to do your VPNs. IPsec allows you to have confidentiality. How does it do this? It does encryption. IPsec allows your information to have integrity. What does integrity mean? It means that the information was not tampered with in transit. Hashing can give you your integrity. You see, when we send it over here, we can do a hash of the information. When we receive it over here, we can do a hash of the information and compare the results. And this tells us that it wasn't changed in transit. Yes, integrity is that ability to ensure your information was not changed in transit. Peer authentication. We want to know that this is router A, and we want to know that this is router B, and authentication can help us ensure that that's who we're talking with. And finally, key management. We want a password over here, and we want a password over here, and we want to be able to exchange that password information securely. And that's the key management that is brought to us by IPsec. So is IPsec busy? Oh, you bet IPsec is busy providing confidentiality, integrity, peer authentication, and key management services. It's not just one protocol that does all that, as you might guess. IPsec is indeed a suite of protocols. Now, when you hear cryptography and cryptanalysis, we're talking about doing two things, folks. We're talking about encrypting data so that someone can't read that data if they were to grab it. And we're talking about hashing. Remember, this keeps our stuff secret so no one can figure out what it is. And this gives our stuff integrity. We know that no one has manipulated it in transit. So hashing and encryption are our two main areas of cryptography that we're interested in. This stuff isn't new. No, it's not new. Julius Caesar did a simple substitution cipher when he was communicating to his military. Thomas Jefferson invented a 26-disk encryption system. And here's a famous one. Arthur, don't know how to pronounce his last name, forgive me, in 1918, he created a machine called Enigma and sold it to Germany during World War II to do encryption. So, if you think that VPNs are built upon new technology, technically they're not. Technically, their technology goes back a long, long ways. Now, we don't need to be master students of cryptography in this class by any stretch of the imagination, but let's just take a look at one way in which you could do encryption, right? Couldn't you just do a character substitution? Yeah, sure, where A, when that shows up in the communication, is actually going to represent E. B, when that shows up in the communication, is actually going to represent F, and you substitute like this throughout. Yeah, this would be a pretty good way to go. And there are substitution ciphers out there that will do this in such a complex manner that they would be tough to break. Here's the thing about any type of approach that you're going to use. Okay, here's the remarkable thing. They can all be broken. Yes, absolutely every type of encryption that you could do today, thanks to the power of computers, ironically enough, anything you could possibly do today can indeed be broken. Yes. The trick is, how long would it take one of our computers to do it? we can do the encryption to such an incredible degree, right? We can make the encryption so strong that it could take, let's say, 50 years to decrypt it. That's strong enough for most purposes today, you see? But if your encryption only takes 2 minutes to break with a modern computer, then you wouldn't want to use that encryption because someone could go through that pain very easily in order to encrypt your data. So everything can be decrypted. It's just a matter of how long would it take. And I think we actually have a chart that shows how long it would take for many of our encryption mechanisms to be broken. By the way, how do you go about doing the encryption? Do you do it in blocks of information at a time, or do you literally do it 1 byte at a time? Yeah, do you do it actually on a bit by bit basis? Well, these are called stream ciphers, and these are called block ciphers. Digital Encryption Standard, DES, is an example of a block cipher. Good old plain DES does 8 bytes at a time of the encryption. Now, here you can see the encryption process in action. We've got some plain text, okay? Maybe we want to send our security policy, right? Yeah, we're going to send our security policy over the internet. Well, we want to encrypt our security policy. So we feed our plain text into an encryption algorithm. An example would be like triple DES. We mentioned DES a moment ago. Triple DES is roughly 3 times more strong. So we feed our plain text into the triple DES encryption algorithm. It is encrypted using a key. Yeah, key is a password. Anytime you see key, just think password. So we have a password we use with the encryption algorithm to encrypt this stuff. Look at what it gets sent over the network as. A bunch of gobbledygook. Gobbledygook being the technical term. We now don't have plain text anymore. We now have what we call ciphertext. Yeah, we call the gobbledygook ciphertext. That is the official word for the gobbledygook, ciphertext. And then we get to the other side of the VPN, and we have a decryption algorithm that, no surprise, uses a decryption key and gives the information back to us in the original plain text. This illustration that you see right here, folks, is very powerful, and this has been the reason why so much data has been transferred over the internet lately. Yeah, because of our ability to do this, make it so that if someone grabs the information, they can't make heads or tails of it. This is the basis for so much of our modern internet transfers. Now, one of the very interesting things when it comes to cryptographic attacks is that they go after that one element that can allow them to read your stuff, the key. Yeah, they go after the key in order to crack the code. That's, there's many of them, right? As you can see, many different styles of attacks, but probably the one that gets the most press and the easiest one for us to really think about is the brute force attack. Yeah, oftentimes these are called a dictionary attack. So you have a password, right? Otherwise known as a key that is used to keep your stuff secure, to keep it cryptographically protected. And what the brute force attack does is it takes a dictionary of all the words in the English language and it starts firing them and combinations of them very rapidly at the password that you have created. This is the main reason why we are told not to have common words that we use as our key. So, you don't want to use a password of tennis. You don't want to use a password of volleyball. You can tell what sports I like. Now, what you can do to dramatically foil this type of an attack is you could do volleyball, but do it capital V, 0, 1, 1, the number 3, large Y, large B, ampersand, 1, 1. So notice there's my volleyball password, but I've done character substitution. Yeah, in the password itself. And could the dictionary brute force attack still crack this? Well, unfortunately, the answer is yes, but it'll take significantly longer to crack than if it was just volleyball in all, simple text. So, lots of different ways they can attack your cryptography, but most of those attacks are going to be against your key used in the cryptography, and we just saw a simple way in which we can really foil many of those attacks in the creation of a nice, strong key. So, we want an encryption algorithm that has built-in resistance to all those known attacks. We want it to support longer key lengths. Think about it. The longer your key is, the longer the password is, the much more strong that cryptography is going to be. We want the avalanche effect, where if there's small changes in the plain text, it causes major changes in the ciphertext. That's a good feature. And we want to make sure that we use a protocol that we won't get in trouble for using. Yeah, the United States government tells us that if we are sending information overseas, for instance, or gaining information from overseas, we can't encrypt it with too strong an encryption algorithm. Yeah, we're worried about terrorism in the modern age, aren't we? So we might be encrypting it so the government can't read it and sending it overseas to guard against the government seeing the terrorist communications. This is a big deal. So there are import and export restrictions, and we've got to make sure, obviously, we are not violating those restrictions when we choose our encryption protocol. Now, it turns out for encryption algorithms, there are two different ways in which they can use your password or your key. There is symmetric encryption and there's asymmetric encryption. Doesn't symmetric mean the same? Yeah, symmetric means the same. And sure enough, the same key encrypts and decrypts the data. Having the same key encrypt and decrypt the data means for very fast cryptography, and this is what we do for your bulk data. Yeah, this is what you do today in the VPN for all of your main data. Asymmetric encryption algorithms use a different key for encryption and decryption, and they are relatively slow. And what we can use them for is to actually protect the symmetric encryption key we want to send over the internet. So we're not going to use this for our bulk data. We'll use it to protect the key itself, used in the symmetric encryption. Pretty cool, huh?